In this video, we're going to be discussing the concepts of linear and angular velocity as they relate to points traveling on circles. In this diagram, we have two circles, the red circle and the green circle, and we have point A on the red and point B on the green. What we're going to be doing is animating these points so that they're traveling on their circles in a counterclockwise direction at the same linear velocity. Now, when we say linear velocity, we're talking about speed as we know it, which could be measured in inches per second, feet per minute, miles per hour. Linear velocity is what we're used to thinking of when we talk about a rate of speed. Now, the reason we know these are traveling at the same rate of speed is that the motion controller at the bottom of the screen is showing us that the speed is 1 for both of these. And we're not sure what the unit of measurement is, but it's the same for both. At this point also, since we've stopped this, we can talk a little bit quickly about angular velocity. Angular velocity means if this point has traveled through a certain number of degrees on a circle in a given amount of time, we can talk about angular velocity. Since point A has traveled approximately through 365 degrees in the same amount of time that point B traveled through approximately 365 degrees, that they seem to also have the same angular velocity. Angular velocity is measured in degrees per second, degrees per minute, radians per hour, that type of unit of measurement. Degrees, which measures angles per unit of time. Now what I'm going to do here is change the size of the green circle fairly drastically, and then we're going to animate these points again. Now again, the linear velocity is going to be the same for both. But what we can see now is that point B seems to be going through more degrees per second than point A. In fact, we can say that point B is going to complete more revolutions, complete revolutions around its circle than point A will in the same amount of time. The angular velocities are very different now for these two circles, whereas the linear velocity, as we can see, is still the same for both. And briefly, we can especially see it in that last little bit of movement. Angle A seems to have traveled through approximately 65-70 degrees perhaps, whereas angle B has traveled to about 120 degrees in the same amount of time. That means that their angular velocity is not the same, whereas their linear velocity, as we've seen on the bottom of the screen, has remained the same for both points. In this diagram, we have the two circles, the red circle and the green circle. The green circle is markedly smaller, and what we're going to be looking at here is 2 points on 2 different sized circles, which are traveling at basically roughly the same angular velocity. Again, if I pause this at some point close to roughly the same angled measurement or degree measurement that point has passed through for both. And again, a little bit past 90 degrees for both of these. One thing I would like to point out is that this is just a demonstration video. There are formulas that we're going to be dealing with in terms of linear and angular velocity and sizes of circles. So there are some formulas that we'll need to be able to use. However, just real briefly, one of the reasons that we can create 2 points that have the same angular velocity roughly is because of the relationships of the radius here, the radii. This radius is twice as big as this radius, and as you notice when we animate these points, their linear speed also has a relationship. Point G is going at 0.5 units per second, and point C is going at a slower linear velocity of 0.25 units, distance units per unit of time. So this is what allows us to create two points that are traveling at the same angular velocity, however different linear velocity, and it has something to do with the size of the circles that they're situated on, of course. And by of course what I'm referring to is the fact that point G does get to travel faster to go through the same number of degrees on this larger circle as point C has to travel. Again, the number of degrees that they're passing through is roughly the same here, which means that point G must be traveling much faster, in fact twice as fast as point C, to be going through the same number of degrees. Now again, this is just for demonstration. There are some formulas that we're going to be exploring in the next video. We've been looking at linear velocity and angular velocity.